this is not what I work on. So I'm advertising something else. And it's something I've been thinking about a little while, which is what's happening with mathematical rigor. Like, what do we do, right? We're not engineers. The rigor of an engineer is that the bridge held up. You built the bridge, it stayed up for, in the case of castles in Europe, 1,000 years, right? That's the proof that what you're doing is right. Everything we're doing is in here. If it breaks, somebody's got to say, hey, it's broken. So, right, so let's talk a little bit about what rigor means. So again, proof is the heart and soul of our subject. But the notion of what it means to give a valid proof of something has changed throughout time. That's what I want to try to unpack a little bit. It depends on the particular time, place, the culture in which the mathematical discussion is taking place. And throughout mathematics' glorious 4 or 20,000 year history, depending on how you look at it, there have been lots of instances of mathematicians deciding that previous versions of what was considered rigorous no longer are, and we have new standards. And usually that comes as a result of math getting broken and needing to be fixed by some method. So just to start, really 4,000 years ago, anybody know what this is? Anybody seen this picture before? Heard of it? So this is called it's got a fancy name. The Yale Babylonian collection, some random number. So this is like thousands and thousands of these clay tablets. They're like 4,000 years old. And this one in particular, if you work out what these markings mean, and you can actually go, when I taught at Yale, I took my students to the Yale Babylonian collection because it was around the corner, and they like show this little rock to you, and you go, come on, this has mathematical significance? You gotta be kidding me. And then a bunch of people figured out what these scribes are, what these little notches mean. And this notch means 1, and that notch means 24, and it's 51, and that's 10, and it's written on the diagonal of a square. And you have to know that they're working. What time is it? We work in sexagesimal also. Time is a layover from this time period. So that's 1 plus 24 60ths plus 51 in the next place in the 60ths, and 10 and so on. And they're getting, way more accuracy. This is what I mean this is why this is mathematics and not engineering. You don't need anywhere near this much accuracy for engineering. You got to stop two places ago. This was an engineering problem. This is mathematics. They had the ability to extract square roots, and he puts it on a square. He knows the Pythagorean theorem. And this is, I'm told, I'm not a historian or anything, but I'm told this is like a student's homework from 4,000 years ago. Okay. So they could compute to incredible accuracy, but we would not today consider what that object is. We see the glimpses of mathematics as beyond the methods, beyond the needs of engineering. This is knowledge for the sake of knowledge. But there was no proof that those digits are correct. There was no rigorous argument of what we would consider mathematical rigor. So you get to, apparently, I'm told, that the earliest recorded proof, something that was like an actual argument, is a rather non-trivial theorem. If I didn't have that right angle there, and I just said, take 3 points on a circle, 2 of them on a diameter, and put some random point somewhere else, and look at that triangle, what angle does it make? You would think, well, it should vary as you move B. And okay, you guys are too smart. It's there's 180 degrees here, so there's 90 degrees there. But how do you actually demonstrate that? How do you prove that? It's a non-trivial theorem. Dallas apparently is the first known recorded proof. Of course, there could have been others in all other parts of the world that didn't survive antiquity. This predates the Pythagoreans by half a century or so. Of course, the Pythagoreans then developed geometry and music and all kinds of other things using the mechanism of proof. But they're still missing a bunch of things. So first of all, the Pythagoreans had their whole system built on the Axiom of Commensurability. If we want to talk about what that is, we can, but then one of them drew that square and drew a diagonal through it and said, wait a second, that diagonal is root 2. But what is root 2? Is a rational number. The Axiom of Commensurability says some whole number ratio from the hypotenuse to one of the sides. What is it? And he couldn't figure it out. And then he said, wait a second, it doesn't exist. So the apocryphal story is that he was thrown in the river for ruining their religion. Anyway, they had a major problem that they couldn't resolve, and eventually had to move away from this axiom of commensurability. But what they did not have, which we recognize today, is the axiomatic method. They would prove this theorem knowing a couple of other theorems. So A would imply B. That's how you know that B is true, because you start with A and then you work your way to B. And then B would imply, how do you know that C, maybe if you work backwards, how do you know that A is true? A follows from C. Oh, okay, that makes sense. But how do you know that C is true? Well, C follows from B. Great. And why is B true? Well, B follows from A. Ah, good. We have reasons for everything. Today we would say, guys, you're begging the question. That's exactly what begging the question is. You're going around in circles. So we eventually recognize the axiomatic method. So this is sort of, now, I'm not telling anything new to anybody here. The axiomatic method, so in the year around 350 or whatever BC, is a book called The Elements, which starts with definitions, then axioms, then postulates, followed by theorems that are derived from those axioms and postulates and basic notions. Anybody know who wrote this? That is what I would have guessed. Also, it's actually Eudoxus, and Euclid stole it 50 years later and improved on it and added number theory, and it was just a better book that survived. And we don't have Eudoxus's book called The Elements. But anyway, yes, Euclid is the one I'm, of course, referring to, but it was, those kinds of ideas were around, and Eudoxus really is one of the key figures there. Say it again. Right, was Shakespeare an actual person? Euclid, I'm not a historian, I'm not going to answer that question, I have no idea. As far as I'm concerned, the historical figure exists because the book has survived and tales have survived and so on. But Eudoxus' version of it doesn't survive. Again, I'm not a historian. This is just what I read and people tell me, and I just trust them. Unlike mathematics, where you don't trust anybody, not even yourself, which is what we're getting to. Right. So everybody knows Euclid's elements, and of course, this is what it looks like. So definition: a point is that which has no part. A line is a length without breadth. The extremities of lines are points, and so on. This is what it looks like. Hopefully, to your modern eyes, you see that this is abject nonsense. So, well, maybe we should talk about that another time. But there's, what does it mean to have a part? What does it mean to have breadth or length? How are you going to define those things? A dictionary defines things in terms of other words that are also in the dictionary. So if you're going to have an axiomatic method, you're going to say, we're going to start from somewhere where you can't even start with words, right? So Hilbert was one of the ones that's like, we must have undefined terms. There are things that are simply undefined, and we're going to build everything based on how they interact with them. All you give is the laws of interactions of undefined terms. Anyway, that's not what I want to talk to you about. Here's this, I just thought I'd throw this up. Here's the famous parallel postulate, the fifth postulate, and why people were suspicious when they saw A, B, C, D, and then E was a paragraph. A is, you can draw a straight, if you have 2 points, you can draw a line. B, postulate 2 is if you already have a straight line, you can put your ruler and extend it a little farther. C is you can draw a circle given the center and a radius. D is a funny one. All right angles are equal to one another. Why do you say that? What is right angle? Excellent. Excellent. So he does define a right angle. A right angle is when two lines cross so that adjacent angles are equal. Okay, so if you have two lines that cross, and this angle is equal to this angle, that's what he calls a right angle. And what he doesn't know is that if two other lines cross and this angle is equal to this angle, that he doesn't have a way of comparing this angle with this angle. That's what that fourth postulate is. And then the fifth postulate, which we state as equivalent versions of the parallel postulate, but really he says, if a straight line falling across two other straight lines makes internal angles on the side equal less than two right angles, then the sum of the two straight lines produced to infinity meet on the side with the two. Like, what? That's an axiom? And if you look at the structure of book one, he spends the first, whatever it is, 40 some propositions. The first 20 only use the first four postulates. And then the next 20, every single one of them uses the parallel postulate. So Anyway, this is a historical aside. This is how we get into hyperbolic geometry, things like this in the 19th century. Anyway, regardless, the axiomatic method continues to be developed in geometry, in arithmetic, in number theory, Diophantus, I mean, there's 1,000 names in here. It passes through Persia to India to China. Eventually, it makes its way into Renaissance Europe, and Newton comes along. Now, Newton, how many of you took AP fluxions in high school? Nobody? Nobody took AP fluxions? Newton doesn't tell anybody what he's doing. He invents calculus, calls it fluxions. He doesn't tell anybody. Leibniz called it calculus. That's why it's called calculus. But Newton invents fluxions. I have a personal hypothesis about this. He knows he's supposed to be using the axiomatic method. Can't figure out how to make calculus rigorous. Why do I say that? Look at his Principia Naturalis. This is where the laws of Newton come from. What does he start with? I can't read Latin. Here's the translation. Definitions. There's 5 pages of definitions. What does he do after definitions? Axioms. The laws of motion. Here are the famous, object. Every object has remains at rest unless acted on by a force. Every force has an equal and opposite. Every action has an equal and opposite. But that's all right there. And then from these things, he derives the laws of motion, the parabolic trajectories, the comets moving in ellipses, and all this stuff, elliptical orbits. Kepler's laws are derived from these basic, and his law of gravity. Right? He's well aware of the axiomatic method, and he loves the axiomatic method, and he wants to, in my opinion, he wants to give a rigorous foundation for calculus the way he envisions it. This actually isn't done until the 1960s with what's called non-standard analysis. By then, we have other ways to make, we've had for 100 and change years, other ways of making analysis rigorous. So it becomes called non-standard analysis or something else that's standard, but really this is the pre-standard analysis. It sort of puts in an axiomatic framework exactly the kinds of ideas that Newton and Leibniz and everybody around them were trying to do. Now, Leibniz doesn't give a damn about rigor, apparently. He's just free to talk to anybody who will listen, write as many books as people will read. He teaches the Bernoullis, Johann and Jakob, and the whole family. Daniel, who's a buddy of Euler, they teach Euler. Euler writes 1,000 papers, all doing calculus in the 18th century. And these thousands of papers over the next century, they're perfectly fine. Everybody's writing papers, they're proving fantastic theorems about calculus. Cauchy comes along and starts making a stink around 1810. And he says, no, you don't know what a limit is. What's a limit? And I'm about to teach Calc 1 next week. I'm going to tell him a limit, the numbers kind of get closer and closer. And if one of, there's usually somebody smart that says, what do you actually mean by that? I can't tell you. Come to 311 or something. I'd love to tell you. But Cauchy is the guy that figured out how to turn, instead of statements about infinity, we don't know how to tame infinity, he turns them into existential and quantifiers. Replace infinity by quantifiers. For every epsilon, there exists a delta. That's it. It's engineering, by the way. How much, if you have a sequence and you want to say converges, how much you want to pay? Give me an epsilon, give me how close you want to get. I'll tell you how much it'll cost, how far you have to go in the sequence before you are within that parameter. It's purely engineering. It's exactly what engineers do. Okay, so Cauchy starts introducing these epsilons and deltas, and then he runs into a little problem. A guy named Fourier. So Cauchy proves this great theorem. You have continuous functions. He proves using his rigorous epsilons and deltas, you have continuous functions. If you have a limit of continuous functions, you will have a continuous function in the limit. Makes complete sense. Fourier comes along and says, I'm going to add up a bunch of sines and make a sawtooth. Who's right? Of course, Fourier is right, but you break math, you got to fix it. So, in fact, this is what you're going to be doing in 501. In real analysis, you'll be really fixing Fourier's ideas don't get fixed until Lebesgue integration. That's what the Lebesgue integral was for. Who was right? In a sense, they're both right. So Cauchy was wrong. He actually implicitly assumed in his proof uniform continuity. Uniform continuity, then yes, limits of continuous functions, uniform limits of continuous functions. But he was right that Fourier's analysis, which was in the Euler style and the Newton style and the Bernoulli style and the style of everybody else, needed more axioms in order to interchange infinite sums and integrals, which are themselves limits. Okay, and that's the sort of the birthplace of analysis. Fourier analysis. Real analysis is born out of an attempt to rigorize Fourier analysis, because Fourier broke math, and because she happened to be there to try to pick up the pieces, but he wasn't quite there. So let's think about this. Here's the bigger picture. 1801, you try to write a math paper and publish it in a professional journal with epsilons and deltas, it's going to get rejected, because what the hell are you doing? Epsilons, deltas, are you out of your mind? We don't know what this is. We don't care. Just do what Euler did. Do it out, you know. But 1901, you try to write a math paper that doesn't have epsilons and deltas, you'll be laughed out of the room. You're not doing rigorous math. What do you know, formalize this. Something happened in that century where the culture of mathematics changed and came to a new understanding of what rigor means. Okay, so here's why I'm telling you any of this. Who the hell cares? We might be in the 1810s, maybe, and this is why I'm talking about this. I'm scared of these things. I never use them. I wrote all my papers without any of this crap. This crap's coming along. You guys might actually need it. You guys might actually want it. I might actually want it, which is why I'm sort of trying to stay abreast of progress. So let me tell you a little bit about these interactive theorem provers. They've been around for 30 some years. And what most of the projects have been, like, for example, anybody heard of the Kepler Conjecture? Anybody know what the Kepler Conjecture is? Sphere packing, right. You have, you know, how a grocer stacks oranges. Like, what's the actual optimal way? You could stack them, like, you know, in a cube, a cubicle in a thing, but you just throw them in and they naturally stack in the optimal way. And Kepler says, okay, that should be the optimal way. But how do you actually prove it? So anyway, so Tom Hales, there's a lot of work on this in the 50s, 60s. People realize that there's a way they boil it down to something that should be a finite calculation, but it's an astronomical calculation. In the 90s, Hales is like, well, we have computers now. Why don't we just do it? So he sits down, writes the computer program, does this astronomical calculation, comes out, and the calculation, you know, pops out. The answer is yes. You solved Kepler's conjecture. It was amazing. All right, I'm going to write this up. I send it to the Annals. The Annals sits on it for 5 years or something. The end of those 5 years says, you know, we threw it to a dozen referees. Every one of them said every part that I checked was correct, but I didn't rewrite the code in my own, you know, it's 10 years worth of work to rewrite the code in your own favorite language and check that the computation is right. So, you know, I did the best I could. So the Annals did something unusual. They published Hales's paper. This is the only time that I'm aware of that they add a caveat. We did the best we could to try to referee this. As far as we can tell, it's right, but we can't 100% match. Now, there's lots of papers in the Annals that are wrong, that have been retracted, you know, so for some reason, for this one, because it used the computers, it's not real. We talk, right? We want to understand. Computers just compute. Well, so Hales didn't like that. So Hales went off and used one of these theorem provers to completely rigorously in the computer formalize every single step in the Kepler conjecture. And a decade later, he had the formal proof. But so other theorem provers look like this. They develop their real numbers, they develop some calculus, they develop some analysis, and then they prove prime number theorem. And then they've developed some discrete geometry, and they just develop all kinds of things, and then they prove Kepler's conjecture, and then they prove things vertically. So it's big spikes, and if you want to start your own project, you're starting on the ground. And what's happened in the last 5 years, I would say, maybe even less, 3 to 5 years. I mean, it's sort of, you know, exponential growth. This is also exponential growth, right? It's with the same exponent. You don't know when it's going to turn like this. So so over the last some number of years, people have been using the lean interactive theorem prover. I don't know that that's better than any others. What's better about lean is the community around lean, which has computer scientists talking to mathematicians, not just proving. The computer scientists also use these theorem provers. They're interested in it because they want bug-free code. Imagine you have code that you run through a theorem prover that tells you, yes, this code is actually, as long as the chip is doing what it's supposed to, the code is also going to do what it's supposed to, and then we have bug-free code. So that there's an important side application to that. I think that's why Microsoft got interested in it initially. But Lean Lean has this tiny kernel, so if you want to go and check by hand that you think Lean is doing what it's supposed to, of course, with Gödel, so Lean can't check itself. But if you want to go and check Lean for yourself, it's a tiny thing, and then everything else is built on top of it. So really, Lean is just a tool, and what's really interesting and important for me is Mathlib, the math library, which is just code that sits on GitHub, freely accessible to anyone in the world. It's maintained by some dozens of mathematicians who make sure that everything that's added to it interacts wholly with everything else that's there. So that instead of the Lean language looking like this, it looks like this. It's sort of everywhere everybody's trying to push out a little bit in some direction. And at this point, it basically has an undergraduate understanding in most subjects. Complex analysis is one where it still needs work. But among some other subjects, some subjects they're well into the graduate. So for example, I think all of 501 is formalized. I think everything you're going to be doing in 551 is formalized. So if you wanted to, instead of teching your homework, you could lean your homework if you so chose. There's just like when you first start tech, and it's like / begin, open curly bracket theorem, close curly bracket, open square bracket, Riemann hypothesis, close square bracket. Like you have to figure out what the hell, how it takes. There's a startup cost, but it now has all of these things. And so what was happening in the other theorem provers, and this is just I'm not an expert on any of this. I'm telling you what my impression is as an outsider looking in. What was happening in the other theorem provers is they could prove complicated statements, like the prime number theorem, about simple objects, like the primes, whole numbers, real numbers. Lean, for a while, was able to express very complicated objects. Like one of the first things Kevin Buzzard and his team did is formalize the definition of a perfecto space to show that something that gets you a Fields Medal in the 21st century can be this code is sufficiently flexible that it can just state the definition of this thing all the way down to the axioms. And then more recently, so again, exponential growth. So Peter Schulze had this theorem that he wrote. He and Clausen were trying to do something called condensed mathematics, and he wants to reimagine sort of our foundations yet again using this language. And he said he proved this theorem that was so complicated and that he's not even himself sure if it's really right. Like he checked everything that he could about it, he wrote it, but he talked to teams of people who were working through these things, and nobody had checked this hard theorem. And so in January of 21, something like that, December of 21, around that time, he was talking to Buzzard, and he said, Buzzard said, "Why don't you pose a challenge to the formalized mathematics community? Can we check it for you when other humans won't?" So he poses this challenge. The challenge is published in the latest issue of the journal Experimental Math. Very proud to say. And unfortunately, by the time we were able to publish it, the lead, or fortunately, I don't know, the lead people had already done the hard part. So this is a Quanta article from, I can't see what that says, July 21, and this is June. Nature and July, and Nature and Quanta covered this in June or July or something. In other words, last summer, 6 months after it was posed, and it was not posed to the lean community. It was posed to anyone anyone who wants to work on this. There's Isabel Koch. There's lots of other not competitors, but compatriots. I don't know what to say. In these communities, and the Mathlib community rose to the challenge handily, and now the whole thing is completely formalized. And you could say, well, how do you trust the chip that it's running on? Maybe you trust the kernel, but you put it on a Mac, you put it on a PC, you put it on a Unix machine. On all of those, you just hit compile and it compiles and then comes out with yes, this is correct. So see, I really think of this stuff not in terms of I don't think that we have that many problems in the correctness of mathematics. Here's what I mean by that. There could be 1,000 theorems that are wrong that nobody gives a damn about. I'm okay with that. I don't papers that are published that nobody checks. The important papers will be checked again and again and again. And every crop of graduate students is one of the best things about graduate students. Every time they come to me with something they want to work on, I give them a paper of mine. And they come back and say, I don't know why this is true. And I go, yeah, you know what I wrote, here's what I meant. This isn't quite right. It's just part of the, you know, but then their paper will not say the wrong thing. They'll still say the wrong thing somewhere else, but not there, right? So we're constantly evolving. Anything that's important will, over time, we'll get to the bottom of it. There's lots of instances in the other direction. A famous example is the class number 1 problem, which he here claimed to have solved. It was published in Mathanella, a very high prestigious journal. And for 20 years, people deemed that it was incomplete. He was a high school teacher. He didn't sort of speak in the same way that professional mathematicians spoke. They published it anyway. And Heegner died thinking that people didn't believe his proof. And a few years later, Stark eventually wrote a paper called On the Gap in Heegner's paper, which basically said, there's no gap. Like he did it and he was right. So anyway, again, things get fixed over time. I'm not saying math is perfect. The instant it's published, the refereeing process has all kinds of issues, as we know all too well. But things do get fixed over time. That's not what I'm worried about. What I'm worried about is when you digitize mathematics the way math labs do. Imagine what happens to anything else that's been digitized: music, dictionaries, Bibles. What Google does with all the books that now you can search for a word. How prevalent the word is over time, and all kinds. There's like an infinite amount of things infinite potential of things that could be done if math can be digitized. Whether it succeeds in being really becoming a tool that's very useful for mathematicians depends on how many people believe that it will become a useful tool. There's a chicken and egg, right? It's a self-fulfilling prophecy. People are like, this isn't really going anywhere, which, right, I'm very opinionated. I don't think it was going anywhere until just a couple of years ago when I started noticing they were really formalizing things that were like, an analysis paper from last year is getting formalized in Lean now, and it's not that much harder. So anyway, let me take the next couple of, any questions so far? I'm going to show you what Lean actually looks like. We'll do some stupid examples.
Yeah, this is insane. Wow. I didn't know that this was happening all around me as math. Yeah.
It's becoming more and more of a thing that people are paying attention to. I should mention, just a few weeks ago, there was the ICM, and Kevin Buzzard gave a plenary lecture on Lean. So mathematicians are at the highest level are taking note. This used to be something like, okay, just gonna, computer checks my homework. Like, what are we doing here? Yeah. Right. But this is getting, it's already serious, but it's potential. We're starting to get on this part of the exponential growth. So thought you would be aware of it.
I mean, the fact that it's teaching it to his undergrads too, that's another cool thing.
Yeah. So it's actually, I think he said that initially the way he got interested in it was as a pedagogical tool. So I'll show you, we should be teaching 300 and 311. You don't know these numbers. 300 is our intro to proof course. 311 is our undergraduate, like, beginning analysis course. And certainly 411, like the next time I teach 411, where everything's going to be on Lean, which maybe is why 411 is like baby rooting, like an actual rigorous epsilon delta analysis, which maybe why they won't let me teach it. They like I said, this is an experiment. I have no idea. Like, I don't work on this stuff full time. I'm still writing my papers by hand, and but I'm keeping more than just a toe. I'm keeping like an ankle, in this direction, because I want to because once it really starts taking off, I want to be able to jump in. I don't want to be just starting to put my toe in once we're here, and then I'm too old and it's too late. Okay,
Do you know what, like the back end, like how does it actually?
okay, so it's the foundation is type theory. One of the things that was holding back a lot of the earlier systems is that they were using Zermelo-Fraenkel axioms of set theory. I always found this fascinating. When I was an undergrad, I took you know, logic 101, whatever it's called. I mean, I learned a bastardized version of logic because John Conway was teaching it, and he just, you know, did whatever the hell he wanted. And but you know, I got the fundamental, the basics of Zermelo-Fraenkel axioms and kind of stuff. And so you're like, okay, all of mathematics is set theory. You have these axioms about what sets you can build up, the natural numbers. You know, you start with the empty set at 0, and the set containing the empty set is 1, and the set containing the empty set and the set containing the empty set is the set called 2, and so on. And like you build up the natural, you build up the rational, you build up the reals. Next course, I'm taking topology. It's like, okay, let's take the space of compact operators on, like, whoa. You know, have we checked any of the Zermelo-Fraenkel things? Like, we can't take, you know, sets of sets is a big, no-no. Like, how, and they don't give it to him. It's like we give this, we pay this lip service to foundations. Say, yes, foundations are very important. Look at all the ways math has gotten wrong. And then let's do topology. Yeah. You just want to do some math. You want to get somewhere. You can't get anywhere if you're constantly trying to like prove some god-awful thing about in Zermelo-Fraenkel system. So that's one of the things that was hurting some of the earlier systems. The newer systems are using type theory. Type theory just says you have this thing called a type. The largest difference as a thinking mathematician is that instead of an inclusion sign, like X is an element of the reals, you have a colon. X is a type of the reals. When you start working with it, you really start getting a sense of what type theory is. I never cared to look at the foundations that far down, but it frees you up to, well, as I'll show you in a second, like it really feels like you're just doing that with a couple of minor modifications. So the underlying, have I answered your question? I'm not sure. Yeah, the underlying system is type theory. And then you have just inference. You know, if P implies Q, if you know that P implies Q and you know that P is true, there's a modus ponens thing that lets you infer that Q is true. And so every single thing at some point has been whittled all the way down to the axiomatic structure. But the beauty of MATLAB in particular is that they have tactics. So instead of trying to do every single whittling by hand, there's like a little bit of AI that will just do it for you. You're like, come on, this should be true, just do it. And it doesn't. So it makes it usable to a human in a way that you can actually do topology and say, yeah, foundation. Yep, good, do it. Lean lets you. Instead of constantly trying to, you know, prove that you're not constructing the set of all sets doesn't thing itself, whatever else. Okay, you want to see how what this looks like? Has anyone seen Lean before? I'm just out of curiosity. Oh, okay. Where'd you see it? I'm curious.
I had courses in, but not in Lean, but I had courses in functional programming. So I got interested in that somewhat, and I tried Lean myself.
Interesting. In a computer science department.
I was my major was computer science and math.
So, but this course
was Haskell.
Okay.
I took 2 courses on so I had Haskell.
But I'm just curious which department was offering this course.
Oh, you mean the university?
Within the university, like there are math courses, and then there's
science.
That's exactly it. They've been doing this stuff for a while. Computer scientists love type theory.
Yeah, it's lambda calculus.
Yeah, lambda calculus.
Functional programming.
Yeah. So mathematician, I mean, this goes back to what's his name? Is it Russell? Who invented type theory? Blanking. I think it is Russell. Turing. Anyway, okay, I'm showing my ignorance.
Is there a proof of type theory course at Rutgers, as in maybe computer science department?
Excellent question. I have no idea, which again demonstrates my ignorance of these things. But one of the best things about Lean is that you don't need to know. And what I mean by that is you just work like a mathematician, and yeah, there's this foundation stuff, you know, again, we should not just pay lip service to it, but we should actually, you know, really be working in the foundations. But Lean lets you do everything the way you're used to while actually keeping it rigorous in this new notion of rigor. That's exactly what, you know, the point that I want to get at. All right, let's prove something stupid. I have lean open, and I've imported data.real.basic. So all we have is the real numbers. Because see, even this, I haven't like I took, as I said, foundations, or when you take real analysis, one of the first things you do is like, what the hell is the real numbers anyway? Right? People got in trouble, like we don't have the axioms for the real numbers. We didn't until Dedekind and Cauchy and so on. Right? So what's the naturals? You have zero, you just declare something called zero that's a natural, and you declare that any natural has a successor. That's it. And then you say that zero plus anything is the thing. And from that you derive everything.
So is that how they construct it?
That's exactly how the natural numbers are constructed in
How do they construct reals? How do they take Cauchy's?
Cauchy sequence, equivalence classes of Cauchy sequences of reals. Exactly as you do it in some rigorous class, and then you forget all about that nonsense and you just work with the real line as you draw it and say all the things that you want about it. But in lean, it actually has to get done, and they did it.
I mean, was that very easy to do? But it doesn't strike me so it's easy to.
Right. So you can go back to like Russell Whitehead, where they try to implement this, and it takes them 300 pages to get to 1 + 1 = 2. Here, it's because of tactics. Like, just fill in this crap. I don't care. Fill it in, and it does it. That's the amazing thing. Yeah. So that's what I've imported. Data.real.basic. Okay. Let's see. I don't know. Let's experiment with this a little bit. So here's the source. No, that's source control. I want to see. Here's the entire. So this source is MATLib, and it's got algebra, and it's got algebraic geometry, algebraic topology, analysis, category theory, combinatorics, dynamics, field theory, geometry, group theory. Right. This is like almost 1 million lines of code here that have been added. So if I go to data.real, and then there's all kinds of things about it, the extended real numbers, so that you have real and infinity, which is useful in a lot of places. There's Cauchy sequences, completions, yada, yada. Let's just click on basic. So here's basic, real numbers from Cauchy sequences. Okay, so, let me pull this over a little bit.
So I have a small question.
Yes.
So do you have any idea as to why people would use Cauchy sequences and not Dedekind cuts?
So you have a couple of choices. You can say Cauchy sequences. You could say Dedekind cuts.
Yeah.
You could just axiomatize a complete, totally ordered field, whatever. They did one implementation, and maybe, I don't know if someone has actually done the others and shown them to be equivalent. This is just the choice that was made.
Okay.
That's what's there. You want to do something else, you're more than welcome to, but MATLib, as far as this is like the new Bourbaki. They're systematizing and sort of declaring what they consider to be mathematics. And so now mathematics is defined as the real numbers. Now, those other things, it's not like they should go by the wayside. We should have, it probably exists. I'm just, again, ignorant of exactly what's in the library. There should be something called Dedekind cuts, and there should be a theorem that says that those are all complete totally ordered field, and there should be a theorem that says there's a unique complete totally ordered field, and therefore those things are all equivalent. Like, that should all be in there. But in this file that I call junk, all I'm doing is saying, okay, just give me the real numbers. All right, let's prove a stupid theorem. Let's prove the squeeze theorem. Remember the squeeze theorem? If you have a function h and a function g, and you have a function f that's squeezed between h and g, and they have a limit. So g goes to, let's say, a limit. This is as y goes to x. Let's say the point is x. And the same thing for h. H goes to L as y goes to x. Then from these two things, we can conclude that f goes to L. Squeezed it, right? F can't get away from h and g, and h and g are going to go in the same number. Let's do it. I think I can do it in, what do we have? 17 minutes. Let's do it. So first of all, it doesn't know what a limit is. I got to tell it what a limit is. Okay, definition, limit. You give me a function from the reals to the reals. You give me a point at which this limit is, and you give me the value of the limit. Okay, then what does it mean to be a limit? For every epsilon, yeah. So this is another thing. This is not actually the definition of limit in MATLib, because they're going to use filters so that you can have limits in all kinds of much greater generality. That's one of my criticisms of them. They do it in almost too much generality, so that someone who's trying to start has a very hard time because they have to get used to these different ways of doing things, whatever. Okay, so for all epsilon positive, there exists a delta so that what?
Yeah, for every epsilon greater than 0, there exists a delta greater than 0.
Very
such
good.
That 0 is less than x minus a is less than delta.
Yeah, so let's say it like this. For all y, if x minus y is less than delta, then
0.1 x.
So you want, yeah, right.
Because
So you want 0 is,
value at that point may not.
exactly. So 0 is less than x minus y less than delta.
okay, so this is a funny thing.
Yeah, because it would make it continuous and.
That's true. I've assumed so. Okay, you want to say for all x that are so this and x minus y, or x doesn't equal y or something. Then what f of y minus L is less than epsilon. Okay, let's put this on one line so you can see the whole thing. And it's very good. So the first thing I like to do in something like a foundations, like a proof course, is to leave off that greater than 0, and then I like to prove a theorem. Every limit. Let's just call it every limit. So if I have any function, and any real number, and any L, then the limit of f at x is L. This would, I mean, the fact that so we're about to prove this, which means that our definition was wrong, right? This means the notion of limit is completely vacuous. Why? Well, what does it say? So okay, here's how to read what's going on. This is the tactic state, which means this is what the computer understands at this point in time. So it understands that there's a function, which is a map from the reals to the reals. There are real numbers x and L. And what we're trying to prove, this means the goal. The goal is that there's this limit thing. Okay, but what does that limit thing mean? Let's definitionally simplify, called dsimp limit. What does dsimp mean? It means for every epsilon, if epsilon's positive, then there exists a delta, so there, all that other stuff, right? Okay, well, how do you prove something that's a statement about for every epsilon? Okay, so give me an epsilon, right? First thing you do, if the statement is for all epsilon, is give me an epsilon. So let's introduce an epsilon. Intro epsilon. Okay, for every epsilon, if epsilon's positive, then, okay, so let's assume that epsilon's positive so that we can continue. Okay, that means introduce the notion that epsilon is positive. Intro eps pos. Look at what it's done in this tactic state. It's given me another real number epsilon, and it's given me the fact that epsilon's positive. Okay, there exists a delta. So now I have to give you a delta. I have to tell you what delta to use. -1. Let's use -1. Use -1. Okay, great. And for all y, so what has it done? Before, and this is the great thing, you can click through, and depending on where the cursor is, it'll tell you the state of things at that line. So at this line, it said there exists a delta so that you have this. And then when I said use -1, it replaced there exists a delta by just making delta into -1 and went to the next thing in the proof. Okay, it says for all y. What should we do when we see a for all statement? Intro, yeah, give me a y. Okay, so give me a y, intro y. And then if this thing is true, then this other thing is true. What should we do? Yeah, give me the first thing. Intro. Give it to me. Okay, so give me this fact. Let's call it H or something. Okay, so now H is these two hypotheses together, and there's a little trick that you can do. This is recursive intro, which allows you to do two things at once. So if the statement, there's all kinds of little things that you're going to learn. So instead of getting a statement that's an and, which is slightly annoying to work with, we now have just two statements. Okay. And now I say ex falso. Ex falso says, ex falso is that false implies anything. So change the goal. The goal was the thing that I need to prove is that f of y is within epsilon of L. And I can say, forget the goal. I don't care what that was. Just make the goal false. And now I have absolute value of x is less than -1, but I know that absolute value, so let's have the fact that absolute value of x minus y is always non-negative. And for various reasons, it's better to use less than signs and lean than greater than signs. It makes one less thing, because a less than b is not equivalent, is not definitionally equal to b's greater than a. And you need to use a tactic called symmetrize to do that symmetry. So it's just better to always use one direction, and they chose the less than direction. So, okay, so I have this statement. So I just said, we have this fact, but why is this fact true? So if I go here, so this is ex falso, and now I want to add this fact. So I have to prove, why is this fact true? Why is this fact true? Oh God, I don't know. Why is the absolute value? There's something that's going to say, there's some mathlib is this big chunky thing, and something in there is going to tell me that it's true. Just search the library search. Yeah, okay. And it's called abs non-neg. Okay, that's it. Search the library, tell me what it's called. It's called abs non-neg. Great, we're done. Goal accomplished. It's very usable. That's exactly what I'm trying to show you. Okay, so now we know that x minus y is positive, and we know that x minus y is less than 1. As a human, you'd say we're done. How do you get the computer to finish it? Oh, there's probably something that, chains these inequalities, and it should know that 0 is less than -1. And -1, by the way, what's -1? Well, -1 is a real number, is the Cauchy sequence of constant -1s that have been implemented. But what's constant -1? It's an integer. What's that? It's the negative natural number. Like, all of this is in there.
So you can search for the library, which has like the groundwork, I guess, from the construction of the reals, and look for the -1 and combine it.
Yep. I don't want to do any of that. So I say there's a tactic called linearith, which says if you have some linear thing that should do some arithmetic and come out with false, it should find it. So I go linearith, done. Okay.
So I guess we can import that. It's already taken into account like the topology on R and all these the algebraic structure and all.
Someone's done that for you. That was really hard work over the last 5 years. That someone's done it. So now you can just, that's it. We proved that every function has the limit L at any number. Wow. Because we have the wrong definition of the limit. We forgot one little thing, which is exactly Devin told us we needed a positive here. And if I change the definition to a positive there, all of a sudden I have a problem. And that problem is, after we use -1, now it wants to know that -1 is greater than 0 and for all. And now we're not going to be able to prove this theorem. Cool.
It's so hard to unlearn things.
When you start doing this a little while, your entire conception of mathematics changes. As you're doing your homework, as I'm writing my papers, I'm like, wait, how would I do this in Lean? I realize that what I'm doing is too technical, and they don't have the thing, have some automorphic representation. I gotta but I want to write it in a way that in 10 years or 5 years or 1 year, when someone comes to formalize this, maybe that someone is me, I'll make my life easier. And it makes the writing of the mathematics easier. And now imagine, okay, so now let's actually prove a theorem. So this was just not a theorem. Let's prove, we're going to do this squeeze theorem, squeeze. We're going to call the theorem squeeze. We have functions f, g, h. They're functions from the reals to the reals. I know that I have this inequality. So let's call this the hypothesis H. And try to make this look a little nice. H is a hypothesis that for all y, I guess we have two hypotheses. I can't write two inequalities like this. So let's make a hypothesis. Let's call this hypothesis f is less than h. For all y, f of y is less than or equal to h of y. And let's make another hypothesis. G is less than f, which is the hypothesis that for all y, g of y is less than or equal to f of y. And I want to know this, that we have these limits. So let's call this hypothesis, I don't know, g-lim. G-lim is the hypothesis that limits g at x is L. And I'll have a hypothesis h-lim, which is that limit of g of h at x is L. Let's move this to the next line so we can see everything. Okay, those are our hypotheses. Am I missing anything? We'll find out in a second if I am. I have three functions. F is below h, above g. G goes to L, h goes to L. And what I want to prove is that f also goes to L. All right. Oh, red underline. Something's wrong. It doesn't know what x and L are because I didn't tell it what x and L are. X and L are real numbers. So I need to be given real numbers x and L. Now there's no problem. So it says, okay, I know that the limit of g at this is that, and the limit of that. Let's prove this. How do you do it? Oh God, okay, limit. Well, let's simplify limit. Let's unfold what limit is. The unfolding of the definition of limit is for all epsilon, right. Okay, so we know what to do. Intro, and actually we're about to do two intros, right? Give me an epsilon and give me the fact that it's positive. So let's do that. Intros lets me do both at once. Epsilon and epsilon is positive. So now I have these two things. By the way, it knows the definition. So the fact that I did this definitional simplification here is not for the computer, it's for me. So if I comment this out, there's no problem with intros. That was just an unnecessary line.
The symbol epsilon has to be the same as.
No. Let's make it Jack, and Jack is positive, and Nick is positive. Whatever. It takes whatever name you give it, right? I know that Jack is a real number, and Nick posits that Jack is positive. I don't know. I'm just giving it names. Yeah, just give it names, random names. Yeah.
So why do you have to say Jack and then Nick pause? So it could just be Nick, right?
It could just be Nick.
So some pauses in like
yeah, foo.
So you're going to read that in sequence, as in read the definition of limit in sequence?
Yes, it's going to read the definition in sequence. So it's going to, when I have a for all and then something implies, either of those is handled by intros. And all it's saying is, give me the name. What do you want me to call this thing?
Okay.
By the way, if I don't put anything here, it'll give it its own name. If I just say intros, that's funny. Okay, I have to desimp. Intros looks immediately if there's an for all.
Okay.
And as it stands now, if I tell it, no, really intros by giving it a name, then it'll do it. But if I don't give it a name, if I just say, if it doesn't literally say for all, then, so this is the kind of thing, clunky thing that you'll learn about it. So if I do put the desimp there, so now it has these things. Now when I do intros, it's going to give me those things, but it's going to give it its own name. I'm surprised it actually called it epsilon, which is what it should have called it. Usually it calls it some like god-awful symbol that you can't access, that you don't know how to type, because it doesn't want you to then later start using that symbol. If it gave the symbol itself, then some later version might give it a different name for that symbol. So it tries to like tell you, no, you should name it. Don't rely on me to name it. But in this case, it named it, epsilon and some hypothesis H. All right. Let's see. We got 2 minutes left. All right. Let's keep going. Okay. So, and then we'll stop. So I'll call it epsilon because I like to call it epsilon, and I'll call it epsilon pos because I like to call it epsilon pos. But you call it whatever you. I have to give it a delta. Let's get that far. Let's give it a delta. Where are we supposed to get our delta? We want to be within. Again, I get it from G and H. So remember what this limit is. Let's remember. So I'm going to say have G lim. When I say have and I don't give it a name, it calls it this. I don't have to name everything. I can refer to it as this. I can have 10 different thises, and when I refer to this, it'll refer to the most recent this. I can also clear things that I don't need anymore in the goal state. I mean, in the tactic state. Okay, so all I've done is I remembered that this is a limit. Now, what's the limit? For every epsilon, so if I feed it, it's a function. If I give it an epsilon, it'll give me a statement. So if I feed into it epsilon, Now this has turned into, if epsilon is positive, then there's some delta. Oh, I have to tell it that epsilon's positive. Okay, so let me feed into it epsilon's positive. Okay, so now it knows that there exists a delta, so the G was within epsilon of L. All right, so give me that delta. You know that I have, this isn't, here I'm trying to prove that there exists a delta. Here, I know that there is a delta. So give it to me. So let's obtain a delta. Let's call this delta 1, since we'll also have a delta from H, and the hypothesis that comes with delta 1. So let's obtain those two things from the fact that G has the limit using this epsilon. In other proofs, you need epsilon over 2 or whatever. You feed all that in. Okay, so we obtained a delta. So now we have a new real number called delta 1, and we have a hypothesis so that, I could break this even further. Let's say H delta 1, H del 1, and little h del 1. Okay, so now I have three hypotheses. Little delta is positive. That was the key thing we were missing before. And then for all y, yada, yada. Okay, any y within this range is within. Fine. We got that one. Let's get another one for h. So there's the delta 2, delta 2, delta 2. So let's use h lim. Okay, so we have a delta 1, we have a delta 2, we've got G and H within epsilon of L. What do we want to make our delta? The minimum. Yeah, we got one delta that said if you're within X of, and then we got another one. I don't know which one's bigger, just take the minimum. So I can let delta be defined to be the minimum of delta 1 and delta 2 and use delta. Okay, I have to show, what do I have to show? I have to show that delta is positive, and I have to show that for all yada yada, the yada yada. So that's two things that I have to show. And right now they're in one goal. And it's more convenient to split an and into two different goals. So that's called split. Split. And now instead of one goal, I have two goals. For the first goal, which ends down here, I have all the same assumptions as before, and all I'm trying to do is prove that delta is positive. And then for the second one, I have all the same assumptions, but now I'm trying to prove this statement.
But you have to prove that this delta will be positive. You can't just use a library from earlier and say minimum.
Well, I'm about to do that. I'm about to do that library search, exactly. So if I put the curly brackets, then it just sort of cleans up the info view, so I don't see the other goals. Let me work on this goal at a time. In fact, let me not work on it at all. I'm just going to say sorry. Sorry is a technical term that says, just pretend I proved it. It says, okay, fine. You know, because you don't always want to work on exactly the thing it wants you to work on. I could do it right here. I could do it from the very beginning. Just say sorry, and then it'll say, okay, you proved it. You know, let's say this is proved. What do you want to do with it? Move on. So it lets you work on whatever part of the proof you want to work on, right? While continuing to check. So now it's got an error because what are you doing? You said moved on, but now you're telling me to do stuff, right? That's what this underline is. Okay, so I'll do one more thing, which is now this is where we're really trying to prove something, which is for every y we're within this range. So I would intros a y, I would intros a y, and I have two things that are going to imply something. So I would intros that, but that's two things. So let me break up those two things. So that's recursive intros, R intros, y, and the two things are, I don't even remember what they are, so I'll call them H, 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 and H, 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 H. Okay, so that x isn't y and that x is between delta. Okay, so then I'll continue with the proof and say, well, why do I have the upper bound? Because I have the upper bound on h, and f is upper bounded by h. Why do I have the lower bound? In fact, let's do that one last thing, and then we're going to stop. How do I convert this into the other thing? Okay, the fact that absolute value is less than epsilon is equivalent to, I want to split it into two things. It's less than epsilon, and its negative is greater than negative epsilon. There's got to be a theorem. That's already in the library somewhere. So this is where the fact that there are maintainers of this thing, they try to keep a very uniform vocabulary. So you should be able to guess. What should this theorem be called? It should be called like abs less, absolute value less than. So let's see, does such a thing exist? Let's have abs less than. So it tells me this, is that absolute value is less than if and only if I have these two.
Oh.
Beautiful. We guessed right. I mean, I did look it up before. But if you didn't know, you go and you know, play around for a second. And so that means that if I rewrite by this theorem, let's use this theorem. So that's called rewrite. So if I rewrite by this theorem, now the goal has turned into two goals. And now I split those two goals into actually two different goals. And now I work on the lower bound using G, and now I work on the upper bound using H. Okay, that's what it looks like. So once you get used to it, just like you've gotten used to typing in tech, doing this is a little bit slower than writing it by hand. But every single thing that it's doing is checking all the way down to the definition of natural numbers. That's why I'm scared. Anyway.
I suppose I can be a little bit more explicit. Like, for example, when I do a proof and I just say minimum of delta 1 and delta 2 has to be positive, right? I'm not really thinking about that. But I guess you have to be a little bit explicit here.
Yeah, so when you first do it, it'll take you like 10 lines to prove. And then you're like, oh, right, there's this thing in the library that lets me call the right thing, and then it just does it. So you get better and better. I mean, I've had a little bit of experience with this, so it looks smoother than if you tried to do it yourself. You sat down and just said, wait, what was there was rewrite, but there was intro, but intros and are intros and split, and where do the curlies go? Like, all that stuff takes time. But then once you have a little bit of familiarity with it, yeah, you just prove whatever theorem you want, just like this.
And they are using DFC here, right?
No, they're just using type theory.
Oh.
Things are not sets, things are types.
Oh, yeah.
But there is CFC somewhere in.
You can prove.
You could do set theory and stuff.
Yes.
Okay.
But could you do another system that doesn't use DFC? Or, for example, that, you know, the mathematicians that don't believe in proof by contradiction?
Well, there's a whole discussion, right? So MATLib does just systematically uses the law of excluded method. Now I don't even know if that's really true. Any part of MATLib that I've ever used does use the law of excluded method, does allow it. You could also make a system that doesn't. You don't have to work in MATLib. Lean is a standalone kernel. It lets you do whatever you want. You can start from scratch and not have access to the million lines of code that someone's already written. But yeah, that's what this.
Now, you say that this is not using sets, this is using type. But I guess I'm having a hard time distinguishing what you mean by type and set. Like when you
because I haven't explained that.
Yeah, because like when you say the word type, it sounds like it's the type of value.